Everyone, you can hear me okay? Okay, perfect. Good morning. So I have no clue about Facebook group. You organize yourselves. I have a Facebook account, but if you ask me to be your friend, it might take a while because maybe I check it once every 6 months. So yeah. Yeah, I enjoyed Facebook before until it became too popular because I'm a hipster, so I don't like when things become too popular. It's not cool. All right. Hi everyone. Nice seeing you all. Oh, yeah, people are still connecting slowly but surely. So I suggest we just start by going back to the previous classes quiz, which was well done, I would say. So let me share my screen. Okay. So you stop me if you have any questions. So I'm quite happy with the answers you gave me. So I think I can give you a quite difficult midterm and final exam since you're a bunch of smart people. So joke's on you now. No, I'm just kidding. I'm not going to. It's going to be all right. Okay, so given the sets S1, rabbit, monkey, elephant, S2, snake, monkey, elephant, and then S3, elephant, rabbit, monkey, S4, rabbit, monkey, which statements are true? S1 equals S3, so everybody said that that was true. Indeed, that's true. Why? Because we don't care about the order in which we write stuff. The only thing that matters is what's inside it. So here we have the same three elements. So good. Is the carrot inside S1? No. So no person said that. Is S3 included in the reals? So two people said yes. So can somebody tell me what they were thinking when they said that? Is an elephant a real number? If it's a variable, then yes, but I haven't specified it. No, nobody wants to own their answer. All right, that's fine. So yeah, so it's not a subset of R because yeah, these things are not real numbers. They're animals or they're emojis, however you want to call them. S4 is a subset of S2. Is that true? No, because the rabbit is not inside of S2. So that's just easy to miss. S1 is S4 is a subset of S1. Yes. S1 is a subset of S3. Yes. Why? Because the set itself is its own subset, is one of its own subsets. So yeah, of course, then if we see that S1 is equal to S3, then S1 is also a subset of S3. Then the empty set is a subset of S4. Yes, because the empty set is a subset of everything. So nothing is inside everything if you want. So that's not too difficult. So you stop me if you have a question. Now, given the sets S1 rabbit M1, S2 snake M1, S3 1 rabbit M, what elements are contained is in S1 intersection S2 in, union S3? So rabbit M and 1. By the way, so when there's a check mark, it means it's a right answer. So let's start with S2 union S3. So I get snake M1 plus 1 rabbit M. So I have a 4-element set. And then intersection with S1. So then again, there's only S3 and S1, and the snake is not included. So 1 rabbit M. Right? So the snake is not inside it, and nobody thought that the beer was inside it. Thank goodness.
I'm sorry, sir.
Yeah, go ahead.
So sorry to cut you off. Would you mind explaining that one more time, please?
Okay, it's just I start with what's inside the parentheses. So the question is S1 intersection, then S2 union S3. So we first start with what's inside the parentheses. So here I have sets. It's not sets of animal or number or letter or anything. It's a set of everything that could be in these sets. We don't care. Just have to define them. So what's the union of S2 and S3? That's so the combination of both. So that's snake, M1, on an M was already there, and then a rabbit. So that's 4-element set, right? And then we take the intersection of this 4-element set with S1, which is rabbit M1. And what do we get? Well, so 1 rabbit M was already in S3, so intersection with M1, that's true. But then the snake was also inside this union, but it's not in S1, so it's not part of it. So the right answers were 1, M, and rabbit.
All right. Okay. Thank you.
No problem. All right. So now, what are, so I think these are the same sets as before. Yeah. What elements are contained in S1 union S2 intersection S3? So let's start with S2 intersection S3. So I get, because that's inside the parentheses, so I get only 1 and M, right? Because the rabbit is not in S2. And then I take the union of 1M and 1M rabbit. So whoop, the rabbit is back in. So again, 1M and rabbit. So most of you got it right. Yeah, the snake is not inside it because it's not in S1. Okay, given any set S and a universal set U, what statements are true. So here it's any set S and any universal set U. So is S union empty set beer? No, because S union empty set is S. And S doesn't necessarily is not, well, beer is not even a set. So, well, I would have to define that beer is a set, but anyways. So good, nobody thought that was true. S intersection empty set is empty set. What is so empty set is nothing. So if I take the common element between nothing and anything, there's just no common element. So that's the right answer. So that's true. S union S equals a universal set. 6 people thought that was true. S union S equals what?
S.
Good. S union with itself is itself. So it's not a universal set. S intersection S is empty set. No. So S inter S is what? Good, it's S again. And S intersection U is S. So this was true. And yeah, most people thought that was true. Okay, all right. So again, congratulations. I'm happy with means you paid attention. Yeah, question, yeah.
The last one.
Oh, last one. So S intersection universal set. So universal set is, so the definition of universal set is all the elements that I can think of right now that I'm considering. So any set has to be by definition inside the universal set.
Okay.
So if I say that, for instance, U is the real numbers, then all the sets I'm going to be looking at, say S, will be a set that contains some real numbers inside it. So S intersection U, well, everything that's inside S is, of course, inside U too. So I get S again.
Thank you.
Okay, no, my pleasure. All right, so continuing with our journey. Now that we are very smart and we understand sets well, let's go on with tuples and pairs and all this good stuff. So, okay. So class 2. All right. So yeah, let's call this relations. And functions. So that's a large topic, something that I'm writing class 2, but of course, yeah, it's probably not going to be exactly fitting into only class 2, but still. Okay, so let's talk about ordered pairs. So just as a reminder, so in sets, so the order elements matters or doesn't matter?
Doesn't.
Yeah.
Yes, does not matter. So, for example, 1, 2 is the same set as 2, 1. But in ordered pairs, or I would say tuples, sometimes you may hear. the order does matter. So example, so we write it with parentheses. So 1, 2 does not equal 2. So what are represented by ordered paired? Anything that I like, anything that I want to represent, to be represented by ordered pair if the order matters. So can somebody give me an example of things that I might be representing with this?
Preferences?
Yeah, references. So
Sorry, preferences.
preferences. Yeah, so in that case, that would represent goods, for instance, like consumption. So I would have, yeah, consumption of good 1 and consumption of good 2. And of course, if I consume 1 car and 2 beers, then that's not the same as consuming 2 cars and 1 beer. So very good. So an example that we see often is coordinates. For instance, X, Y, Z. Equals, say 1, 2, 3. Or yeah, so baskets of consumption. Yeah, so consumption. Bundles. Like if I consume good 1, good 2. Equals so 1 cat and 4 cars. I don't know. Yeah, and we could give an example. So example for coordinates. All right. So if I have, for instance, let's do this like this. So this is X, this is Y. So if I have the point, so this would be 2, this would be 1, this would be 1, 2. So of course the point 2, 1 isn't the same point as 1, 2. Okay. Okay, I'm going back, sorry. Here it is. So I got the point 2, 1, which is not the same as 1, 2. So that's quite obvious. Now, so question about this. It's really a definition that we should be somehow familiar with. Okay, Cartesian product. So we write it this way. So by the way, this cross sign is a really overloaded symbol in mathematics. So if you see it in one context or the other context, it doesn't mean that it's the same. So if you say, for instance, I don't know, 2 times 1 equals 2. So that's you use it in arithmetic. It has equivalent to its multiplication. So like this is the same. Here, Cartesian product for sets, it has some specific meaning. All right, so it's the set of all possible ordered pairs. Produced by the elements of 2 sets. So for instance, if I have set A, sorry, equals 1, 2, 3, and set B equals 4, 5, then A cross B is equal to a set of ordered pairs, which would be 1, 4, 1, 5. Oops, sorry about this. Then second element, 2, 4, 2, 5. And third element, 3, 4, 3, 5. So if A has n or m, let's see, elements, and P has n elements, then A cross product B has how many elements?
Mn.
Yes, mn elements. So this, so why do we, what is that good for? Well, you're going to see that it's very good to define large sets of numbers. So for instance, if x equals r, so x is a set that contains all the real elements, and y equals r, then x times y equals, so let's write this in set element. So it's going to be, so can I enumerate all the pairs? No, even if I have all the time in the world, since there are an infinity of possible pairs. So what I can say though is I can describe it. So it's going to be a set of ordered pairs, x, y, such that x is element of R, and Y is an element of, oops, R. How do we write this? We write XY is an element of R cross R times R, which is equal to, so how do we write it? If you have seen this sometimes in some mathematics context, R squared. So when we see something is R inside R squared, we're using this notion of Cartesian product. It's an element of this larger set, which is a combination of all the possible numbers that X can take, which is R, and all the possible numbers that Y can take, which is also inside of R. So we just write it inside of R squared. And of course, we can extend the concept to XYZ, which will be element of what?
R times R.
R3?
R times, yeah, R times R times R, which would be equal to R cube. So in this case, I'm in, of course, 3 dimensions, so it's harder to draw stuff. And also, I can even go one bit further and just say that we can have X, which I'm going to write X1 to Xn, yeah, with commas. And here I'm going to write this in bold just to see that it's not a scalar, it's a tuple of n elements, which would be element of R n. So if you work in n dimensions, then you are even more abstract. I remember I had a linear algebra class in computer science at McGill once, and we always worked in Cn. So everything, every day was in Cn. I couldn't stand it anymore. It's just so abstract, but apparently you can deduce a lot of stuff in Cn. So everything was about functions and proofs and stuff. Yeah, a whole lot of fun. All right. So now, what do we use this for? So a good thing is to use it for geometry. So a straight line is what? Is a set of ordered pair. In R squared. So for instance, if I say an ordered paired XY, such that, let me use some equations. So for instance, X equals, Y, sorry, yeah, equals 2X plus 3. So that's in set notation. So what I'm saying is I have some pair here. Yeah, and here I already said that I was working in R square, so I'm not going to say such that X is the element of R, Y is the element of R, but yeah, and XY is the element of R squared, but because I've already said it. And there, here what I'm saying is, such that there's some restriction. So I'm not including all the points in R squared. I'm saying the points I care about are the points that satisfy this equation here. So how should I draw this thing? So that's something you may have done in the past. So how do we, what's the trick to draw a line?
Isn't it like 2 points?
Yes.
Set
So
X and Y both to 0 and then connect those points.
yes, exactly. So you can use any point you like, but using 0 is perfectly good. So replace X by 0. Compute Y. Which would be then, we get what? We get 0, 3. And replace Y by 0. Compute X, and we get what? Can somebody do it? Or it's too early in the morning?
3/2.
Yeah, 3/3. Three halves.
Isn't it going to
Okay.
be like negative?
What?
Isn't it like negative? Because then +3 would equal 0.
Oh yeah, minus 3 over 2. Yeah, it's too early for me to. All right, so let's try that. Not this. Right. Are you seeing the graph as that we had before? Not sure if my.
Yes.
See the new one, the 2x plus 3.
Yeah, okay, that one. All right, so that's what I wanted. Okay. Yeah, I'm getting used to having this this zoom bar there that annoys me, but so yeah, I'm drawing this, but maybe we. So what points do I want? I want y equals to x plus 3. So I want 2 points, 0, 3 and minus 3/3 0. The tree has 0. So 1, 2, 3 here. Oops. Yeah, so 3 divided by 2, so that would be there. And I get my line. So if you've already done that in the past and you think it's easy, then good for you. It's going to be easier for you in the future. Oops. All right, so that's what we get. Then, by the way, if I have, something I should have done that I will do is label my axes X, Y. Oh, yeah. Things are not working as intended this morning. Sorry. Okay, good. So that's our line. Now, if I was asking, what about? Let's just say X equals Y divided by 2 minus 3/3. So what would that look like?
I think it would be the mirror, a mirror line, like symmetrical about the y-axis.
All right, so let's check 2 points. So I would have, 0 and Y would be 3. And I would have,
Or no, sorry, it's the same line.
yeah, it's the same line. So I was, so that here, the trick I said that I did was to flip the X and Y. So yeah, so what's saying there is this is just a definition, but it's not a unique definition. So as long as these points represent exactly the same set of points, then the line is going to be exactly the same. Yeah, so same line, which verifies the same equation. So this is, it looks trivial what I just did, but it's super important because where we're heading is linear algebra. linear systems of equation, what represents a system that we can solve, that for which we can find a unique solution. So it's important that you see this. Or one thing I could say too is what about 2x equals y minus 3. Well, again, that's the same line. Because if I substitute x by 0, I get 3. If I substitute y by 0, I get minus 3/3. So same line again. So you cannot invent a new line by just multiplying everything by something, or by adding some constant on each side, for instance. It's the same line again. So it's not a different set of points. So that's what we care about. See, are you defining some different set of points or not? If your definition is equivalent, then it doesn't matter if you write it slightly differently. If you represent the same set of points, it's the same line. Okay. So now inequalities, real quick. So say I have something like, let's have the same equation. So xy such that x is now, we had equal y over 2 minus 3/3. But now instead of equal, let's have like smaller. So how should I represent this? How do I know what's inside it or not?
You'd have like an area under over the graph. In this case, it would be under, and the line I think would be dotted to show that it's not included.
Oh, well, that's awesome. I couldn't have said it better. So let me share my screen again. Hopefully now it's going to work. Yeah, what I'm going to do is yeah. All right. So what we said here is, yeah, the equation was x smaller than, so this, we don't use this anymore, x smaller than y over 2 minus 3/3. So this, I can put dotted line, because I know that the points on the line are not included because it's a strict inequality. And then to know which point is part of the set or not, yeah, I can, if I use my deduction, I can guess. But one trick I'm going to give you is simply ask yourself, oh, is that point inside it or not? Or is that point inside it or not? So one point we could ask is 0, 0. So is the point 0, 0 inside the set we're describing here or not? Well, let's just try. So if we substitute with 0, 0, we get 0. And is 0 smaller than minus 3/3? Yes or no?
No.
No. So we know that 0 is not inside it. So then we have made a wrong guess. So no. So we know that this point is not inside it. So the points inside it are the points on the other side. Like this. So that's a good, oh, yeah, I'm sharing my screen, right? Okay. All right, so that's an easy way to draw some inequality. So you check. So it's sometimes you can ask yourself, okay, so because sometimes maybe y is on the left side or the right side, so you can deduce stuff, but just having some systematic check. So is 0, 0 inside it or not? Oh no, so I know it's not part of the graph. All right. So questions about linear equations? Okay, so if everything is clear, we can go to higher powers. We're not talking about God or some other divinity, but powers of X. So higher powers. So for instance, quadratic relations. So I could have something like x equals y squared, or y equals, I forgot my shortcut for plus or minus root of x. How do I draw such a thing?
One is just the inverse of the other one.
Yes. Okay, so if you know the shape of one, you can know the shape of the other. So, but what if I gave you something you haven't seen before? How would you go about and draw it?
Just choose some points for X and then compute their Y values and then plot them out and connect them.
Yeah, exactly the same thing. So to plot it, or to draw the graph, choose some points. So how many? I would say more than 2, right? Because it's a quadratic relation. So let's just say 3 points. If you're not sure, you can always add more. Add more. Okay, so what points? So I could have. Can I choose x equals -1?
No.
No, so I'm constrained. I have to at least pick something that's inside my relation. Anyways, what I can try is if I can, I try -1 and I see something squared equals -1. Yeah, I'm not in R anymore. I'm in the complex territory, so we're not going there. So let's pick, say, 0, 0. 0, 0 is inside, because if x is 0, y is 0. Then if y equals 1, then x would be equal to what?
1.
1. And if y equals to -1, x would be equal to
1.
1 again. So we have 3 points. You can pick the points you like, but I suggest choosing simple ones. So we have 3 simple points. So let's go ahead and draw our curve. Yeah, let me just stick close to the origin, having some things. So this is X, this is Y. I can have this is, yeah, it's not the best time. I'm going to draw something bigger. So imagine that this is 1. Okay, so yeah, I'm just going to use some other paper, some other abstract paper. Okay. So let's see, this is 1, this is 1, this is -1. So I get 0, 0. -1 and -1. And then I can do my best. Let's use some blue and draw this shape. So that's not too good, but it's not art school. As long as we get the gist of it, it's fine. So that's my curve. So again, it's yeah, it will be a parabola, exactly. Good, Omar. Oh, I didn't label my axes. That's bad. This is Y. This is sorry X, and this is Y. Okay, going back to what we were doing. All right, so this is what we call, yeah, I should have, yeah, this is a relation. So relation, any set of points describing, yeah, any set of points in Y, yeah, in, yeah, okay, yeah, actually, I haven't looked at what the exact definition, mathematical definition of relation is. Sorry about this, because we don't care all that much about relations. We care more and more about functions, but still. Okay, yeah, that's just it. It's a relation. Yeah, a relation is a relationship between sets of values. Yeah, so it's super abstract. It's anything we want. So it's not easy to define. But what we care more about is functions. Oh, Azim said, relation between two sets is a collection of ordered pair containing one object from each set. Oh, yeah, that's good. All right. So I'm going to steal your. Oh, I can't steal it. Well, yeah. All right, so this is fine too. Anyways, we don't care all that much about relations. What we care more about is function. So what's so special about functions? By the way, so is this a function or not? A function between, yeah. Could we say that y is f of x here? In this case?
No,
Why?
because each value of x has two y values.
Yes, exactly. So here it's not a function between, because I can find some value of x for which 2 points are answer to the definition that I've just said. And what's special about function is that for each value of x correspond at most one value of y in the relation. So let's see, a relation such that for each x correspond a unique y value. And we can also, so we can write it this way, or also sometimes we say it's f such that x is mapped onto y. So in that case, we would say it's a mapping. And y is the map. Let's see, other notation. But you must be more familiar with this one. So is the previous relation a function? No, because for instance, we had x equals 1 maps to y equals 1 or -1. Yeah, I shouldn't even use map. So with 2, x corresponds y equals 1 or y equals -1. So what? How do I correct for it? Well, what I could do is just drop one part of it and just use y equals square root of x simply. So this is just the positive part, and in that case that works. Or y equals x squared, that works too. So in that case, for each value of x corresponds a single value of y. And let's add some definitions. So the argument is X. The value, I saw you, is Y. Yes, Mr. Adams Gilstrom.
Yeah, I'm just thinking if y equals square root of x doesn't work because we're saying that, or y equals a positive negative square root x doesn't work because two values of y come from one value of x. We're with y equals x squared, we're basically switching that relationship where x can equal positive and negative 2, for example, and y is 4 in both of those cases. So wouldn't that also stand that it's not a function?
So it's what we would say, it's not one-to-one. So that's, we're going more deeply into math there. Yeah, so what the term is, if a function is, yeah, if there's a single argument of x that corresponds to a single image of y and a single image of y that corresponds to a single argument of x. So this, you see, it's both one-to-one and unto, and in that case, that's bijective. Yeah, but this is, yeah, I'm really don't want to torment you with the math terms there, but yeah, there's a difference. So really, to answer your question, is it matters how I define it. So here I'm saying y is a function of x. I'm not saying x is a function of y. So if I was saying x is a function of y, then this would be wrong. This wouldn't be this wouldn't correspond to a function.
Okay. So it depends how you define it. What
Yes,
is the
exactly.
function of what, and based on that we could
Yeah,
say.
so we say the argument is x and the value is y, and there's a single value for each argument, but there might be different arguments that give me the same value.
Okay. Thanks.
Good question. All right. The domain. So this is all for me to speak better to you, but yeah, who knows? Maybe I could ask you this in the exams, but it's not my favorite type of exam question. So I'm defining terms mainly to make things easier. But yeah, so it's good to know them. So admissible values of x, for x. And the range. Are all possible values of f of x given f and the domain. So here the domain, I can constrain it or not. So for instance, the admissible domain for, if I only consider the reals, then the admissible domain, yeah, so a domain could be positive values for x, but I could also say, oh, I consider just x values equal or larger than 1, for instance. So I could choose to describe my function this way. And then the range, what is the range? Well, it's all the possible values that I could get from the domain that I specified and f itself. So for instance, here, could I get value of y in the range of, say, -1? Yes, no, quick.
No.
Yes, exactly. So no, I couldn't get a value of -1 because whatever it is in my domain of x, I'm never going to get a negative value of y. Since the domain of x here only include real values, but if I said something like the values of x include complex values of also, then that changes your answer. In that case, you would say, yeah, you could get -1, for instance. So again, the range is a function of both what possible values I consider for x and what is my function. And I could say also note, not to be confused with another expression you might have seen, codomain. Which may be larger than the range. So this, I'm never going to use this expression, but you could use it, know that it exists. So this is saying, oh, the possible values of y that interests me are, say, from -1 to infinity. And then maybe I'm going to get some f of x that is going to give me -1, or maybe not, but it's just something I choose to define. It's all terms. It's, yeah, lots of definitions today, unfortunately. But yeah, we have to go there. And this is just to prevent some questions if I have one. Okay, so just to see if we are all on the same pages, all on the same page. So if my function is y equals square root of x, what is the possible domain and range? So I would say xy element of, so I only consider the reals. So what's the possible value of values of x? The most I could think of.
All positive values?
Yes. Are, I would say, plus. That's a shortcut. And if I have r plus as a domain, then what will be my range?
Wouldn't it be the same?
Yes, r plus as well. So here I'm saying that my function is square root of x, so only this part here. So what possible numbers can I have for x? Well, I can't have negative ones, so only positive ones, r plus. And as a result, what is going to be my my range? It's going to be from 0 to infinity, so r plus for y2. Then if I have y equals r squared, so Oops, not cube, sorry. Yeah, I could have cube too, but it's less interesting. What are the, yeah, what maybe I should use R because I'm talking about two things.
The domain is all real numbers.
Yes, and the codomain, or not the codomain, sorry, the range.
All positive real numbers.
Yes. All right. One thing to say about economists. So in general, economists don't specify stuff too much. So in math, we were more specific and rigorous. Yes, in that case, it does. If we're talking about natural numbers, it's open to definition, but usually we say it does not. Yeah, but real numbers, we say, yeah. But I could always define it as I like. So I could say something like X such that X is in R and X isn't 0, for instance. If you want to specify, or you could also, this would be equivalent to saying that X such that or X is larger than 0. And if I already said that I'm just interested in R values, so I can just write this actually. So that would be a very, very easy way to write it. So, you know, there's that's something that I find scary in a way in math is we can always be even more precise and add even more details to be sure that everything is super clear. So like professional mathematicians, they know exactly the right amount of details to add. Here, what I'm going to ask of you is just to be nice with me, and when you answer something, put as much information as you think is necessary so that your answer is clear. So when we, for instance, we know we're talking about the reals, then you don't have to say it all the time, it's reals, it's reals, it's reals. But when it's part of the question or the part of what I'm interested in, so of course, then it's good for you to say that I'm talking about real values, for instance. All right, so economists do not specify the domain and codomain. When they are obvious. So for instance, input or production or GDP or many, many different things. So, yeah, so these things are all positive. So I'm not going to say, oh, by the way, input cannot be negative. You cannot use -1 worker. But I'm saying that because I used to teach at a statistics school, and question came sometimes, oh, I cannot really answer your exam question, sir, sorry, because you didn't say whether the number of workers was positive or negative. Well, take a chance and assume it's positive and see where that goes. Yeah, so economists are scientists in general. Yes, research papers or even textbooks, they are long, they have many pages and many equations. At some point, you could always spend an extra page just to specify all the details. But if they're obvious, at some point, you respect the intelligence of your reader, and you understand that we're talking about economics, and that reader is another economist who understands that in real life, you cannot use a negative number of workers, so it's okay not to specify it. All right, so that's good. Oh, by the way, so it's 10. So let's go until 10. When did we start? 8:45. So let's go until, so when did we start stop for a break last time?
At 10. From
At
10 to
10?
10, yeah.
Okay, so